In our last lesson of Unit 2, we're going to look at two different concepts. One of them is the linear approximation, and then the last one is Hopital rules. Alright, so our goal for today is for you to be able to explain why and how we use tangent lines of a function to approximate a function value, and also to determine if our approximation is over or under. Why do we use linear approximation? Well, lines are nice functions. We want to use lines to approximate nonlinear functions, nonlinear differentiable functions. What does that mean? Well, another way to simply state what that sentence tells us is we can use lines, more specifically we can use tangent line to approximate function value near the point of tangency. And the reason why we use lines is because lines are a lot nicer to use than nonlinear functions. So in order for us to use lines to approximate functions, more specifically, we are using the tangent line. Remember that the equation of the tangent line, which is y equals to mx plus b, once you have, plug in your slope and plug in your point, you simplify, is used to approximate the value of the original function near the point of tangency. So this is the point of tangency, so you can approximate any function value using the tangent line, because the tangent line, especially near the point of tangency, is pretty darn close to the point on the function value. Hopefully that is not too hard to understand, but if it is, maybe example 1 will really clarify what I'm trying to tell you here. I want to write an equation of the tangent line to this function, which is a cubic function, at the point 2, 8, and I want to use the tangent line to approximate the function value near 2. Okay, so the function value, these values are the x-coordinate that's really close to 2. I'm going to use the equation of the tangent line to approximate the function value. So the first thing I need to do is I need to find my slope of the tangent line. That can be found by taking the first derivative and then plug x equals to 2 into the first derivative. That is gonna give me 12. So the slope of my tangent line is 12. I have the slope, which is 12. I have a point, which is 2 and 8. That allows me to come up with my equation, which is y minus y1 equals to m times x minus x1. Simplify and solve for y. My linear equation is y equals to 12x minus 24 plus 8. That brings us to minus 16. This is the equation that we are going to use to approximate the function value. So the function value at 1.9 is about, remember that we are approximating, so we're not getting an exact answer. So the function value at 1.9 is about replacing 1.9 in for x, we get 12 times 1.9 minus 16, and that brings us to 6.8. So 6.8, okay? What is the exact value, you might wonder? Well, the exact value of 1.9 can be found by plugging them in here. This is the exact value. This is the approximated value. If you were to plug 1.9 in, you would get 1.9 raised to the third power, and you would get 6.859. That's the exact value, and this is the approximated value. We didn't want to use the original function because the original function is non-linear. the tangent line is linear, but notice that the tangent line does a pretty darn good job of giving us the function, the exact function value. We're off by 0.059, which is a very small value. All right, so what is the approximated value at 2.01? To find the approximated value, you use the tangent line, because the tangent line near 2 gives us that value. 12, 2.01 minus 16. And that comes out to be, using a calculator, 12 times 2.01 minus 16, 8.12. 8.12. Just curious, but what is the exact value at 2.01? To find out, we plug 2.01 into this function, and then we raise it to the third power. 8.120601, and that's pretty darn close to what we found using the tangent line. Okay, so guess what you did? You found an approximation for the function value. This is the function value using the tangent line. If you want to find the exact value of these, then you plug them into the original function. But the purpose is, is it possible to use the line of tangency to approximate the function value? The answer is yes, and they are pretty darn close to the real value. Okay, if you look carefully at the graph of x cubed, the graph of x cubed looks. Let me see if I can get that graph for you. Zoom 6. The graph of x cubed looks like this, right? And so the tangent line. This is the graph. This is the graph of x cubed. So the tangent line at x equals 2 right here looks probably like that. Looks like that. I want you to note that the tangent line is actually below the graph. This is the tangent line, right? It's below the graph. Okay, it's below the graph. And when we try to approximate the value near 2, we use the tangent line because it was easier to evaluate, and it gives us a value that's pretty darn close to the original value if we were to plug in the function. But keep in mind that we had a value that was using the tangent line approximation. We had a value that was actually less than the real value. Now, if that confused you, just go back to this first scenario. We knew that the approximated function value is 6.8 using the tangent line, but what was the real answer? Well, the real answer was it was 6.859. In other words, the real answer, it's right here. The real answer was clearly higher than the approximated answer, which kind of makes sense and is supported by this graph, because if you look closely at this graph, the equation of the tangent line is below the original function, and therefore the output, the approximated value, will be less, or we call it under, the exact value. All right, and that brings us to kind of like our next concept. How do you know when you have an over approximate or an under approximate? Well, that kind of depends on where your tangent line lies. Say if your curve is an upward facing curve at the point of tangency, what that means is, like, let's say if this was the point of tangency that we're looking for, if this was the point of tangency, then the graph is actually facing up, and that implies that the tangent line to that point has to be below the curve. See? And if our tangent line is below the curve, then our approximation of the function value will lie below the actual value, and we call that an under. This is the approximated value. This is the real value, right? Clearly, if our line is below the graph, if the tangent line is below the real graph, then the approximated value will be less than the real value. Okay. Similarly, if our graph is like this, and our point of tangency is where the graph is facing down, then the tangent line will clearly be above the graph. And if it's above the graph, then our approximated value, this would be an approximated value, will be higher than our actual value. We say that's an overestimate. All right, now the last thing we want to discuss is called the Hopital's rules. Hopital's rules takes us back to Unit 1 because it gives us a technique on how to quickly evaluate limits. Now, if you recall, evaluating limits in the first unit was actually kind of challenging because there are times where you do direct substitution and you get either one of these. And when you do, these are referred to as indeterminate forms. If you have forgotten indeterminate forms, then please go back and review indeterminate forms. But anyway, when you get one of these, you get what's called an indeterminate forms. And we had like 2 other techniques that we can try to work through indeterminate form. It's called factor and cancel. Another one is called rationalization. If you encounter either one of these indeterminate form. Well, and by the way, I couldn't introduce Hopitals to you before Unit 2 because it requires us knowing how to find a derivative. So what does Hopital tell us? Hopital is a rule or a technique to easily find the limit, guys. You can find the limit of almost every function quickly and nicely if you know how to use Hopital's rules. So you don't even have to do these techniques anymore. All right, so here's what Hopital tells us. It tells us that if you want to take the limit as x approaches a number, and it has to be a fraction, okay? It has to be a quotient of 2 functions, okay? If you are taking the limit of a quotient of 2 functions, and if direct substitution gets you 0 over 0 or infinity over infinity, if direct substitution yields 0 over 0 or infinity over infinity, then Hopital said, Hopital's rule tells us that this limit is identical to the limit of the derivative of the top over the derivative at the bottom. But you take the derivative independently. Do not use quotient rule. I repeat, do not use quotient rule. Take the derivative independently. Okay, let me repeat what Hopitals tell us. Hopital rules tells us that if the limit of f over g yields 0 over 0 or infinity over infinity through direct substitution, then the rule guarantees that this limit is the same as the limit of the function derivative. And then plug in a to find your answer, okay? Which equals to f prime of a over g prime of a. Very simple and very easy. Let me take you through a few examples to show you how easy it is to use Hopital's rules. Consider this problem, back to the limit problem. If I want to evaluate this limit, the first thing I'm going to do, I'm going to try substitution. So, substitution gives me zero over 0. If you see this, then you use Hopital's rules. So use Hopital. What does Hopital say? Hopital tells us to take the derivative of the top function using just the power rule. And the derivative of the top function is going to be 2x, ladies and gentlemen. And he also said take the derivative of the bottom function, which is gonna be 1. Okay. To find the answer, you just have to now plug 2 in. And if you plug 2 in, you get 4. That's it. That's what Hopital tells us. Techniques on how to take techniques on how to find limits using derivative. Okay? It's very easy. Do not overthink it. Do not overthink Hopital's rules. Let's do another one. I want to evaluate this limit. First thing I do is I'm going to try direct substitution. So I'm going to plug that in there. I'm going to plug 0 for that. So what do I get here? I get 1 minus 1 over 1 minus 2. And this is 0 over negative 1. Now, this is not Hopital's rules, okay, guys? 0 over negative 1 is just 0, and that's our answer. Hopital's rule only applies when you have 0 over 0 or infinity over infinity. If you plug it in and you simplify and it comes out to something nice like this, then it's just equal to 0. Good job. Let's go to this last one over here. Try to plug it in. What do we get? We get, if you plug infinity in here, then you're gonna get infinity over infinity. Okay. Hopital is activated for this particular example because we had infinity over infinity. So what does Hopital say? Hopital tells us that go ahead and take the derivative of the top function. Guess what that is? 2x. And also take the derivative of the bottom function, which is going to give you 6x minus 3. Okay. Do a direct substitution. What do we get? If you do a direct substitution, you're going to get infinity for the numerator because 2 times infinity is infinity. If you do a direct substitution for the bottom, you're still going to get infinity. Okay. Guess what? Hopital's rule is activated again. So we take the derivative of the top again. What does that give us? That gives us 2. Good. Take the derivative of the bottom, and that gives us 6. That simplifies to 1/3. So we're done because supposedly the limit of 1/3 is 1/3. And there you go. Hopital tells us use derivative to find the limit. Now, if we go back to number 4, notice that we could have used we could have thought of this as finding the horizontal tangent line. And isn't it the limit is the coefficient since the power are the same? So 1/3 would have been your answer. But the nice thing is we just showed that Hopital actually works. Hopital works for every problem as long as direct substitution, you use either infinity over infinity or 0 over 0.